Today our focus is going to be on how do we take the derivative of inverse functions. Inverse functions is going to be the focus of our study. So I want you to take a minute for yourself and pause the video. See if you can write down what you know about inverse functions, verbally, numerically, graphically, analytically, through the 4 different lenses. Pause, write down some information for yourself from your head. Pause now. All right, now that you've had time to think, we're going to talk about some questions for the day. This lesson was created from Mrs. Lemke, who's my buddy here. She's a Calc BC teacher at Lake Forest, and we'll talk more about buddies today. It's kind of our theme. All right, so questions for the day. First of all, what is an inverse function? An inverse function is a function that undoes another function. Okay, so it's not the opposite, it's not the reciprocal, it's the inverse. It undoes the operation of the other. So, for instance, addition and subtraction are inverse functions. Multiplication and division are inverse functions. Logarithms and exponentials are inverse functions. Sine and sine inverse are inverse functions. How do you find the inverse? We switch all of our x's and y's. So all of our domains become ranges, and our range becomes our domain. So we switch our x's and y's, and then we solve back for y. This was in your review from pre-calc. What does the word monotonic mean? Well, that word monotonic we talked about a few weeks ago. Added to your lexicon. Monotonic means strictly increasing, which means that f prime would always be positive, or strictly decreasing, which means that f prime would always be negative. And then that word monotonic is also used in mathematics to describe something being one-to-one. So a function being one-to-one is that for every in, it maps to exactly one out. That's what makes something a function. Monotonic, or one-to-one, means that for every out, there was only one in. So that was that idea of x squared is not monotonic. It is not one-to-one, because if I asked you, hey, what input created the output of 9, somebody could have told me 3 and somebody could have told me -3. That wouldn't work. The visual way of seeing a function is passing the vertical line test. The visual way of seeing a one-to-one or monotonic function is, does it pass the horizontal line test? And again, a parabola would fail that. Geometric connection. We all studied geometry for quite some time. The geometric connection between f and f inverse is there is a reflection over the line y equals x. So oftentimes we talk about reflections over an axis. Here we're reflecting over the line y equals x because if you look back at question 2, we're switching all of our x's and y's. So everything that was a y is now an x, and everything that was an x is now a y. So we've reflected. And now here comes our key for today, and that is the concept of a buddy point. So if the function has a point a, b on f of x, then on its inverse function, sorry, my computer panicked there for a second. Inverse function, we would anticipate seeing the point b comma a. Okay, and we've seen this a lot with inverse relationships. Think about your exponentials. E to the x has the point 0, 1, but natural log has the point 1, 0. Okay, so we have that inverse relationship, buddy points. So if we look at a on f of x, that becomes the output at b on f inverse of x. Okay, here's some typed up information for you so you don't have to jot it all down. A function f will have an inverse if and only if, that's a strong mathematical statement, f was one-to-one. Okay, now everything has an inverse, let's be clear about that. But not everything has an inverse that's also a function. That requires having passed the horizontal line test. Again, go back to that idea of a parabola. That parabola has an inverse. It looks like this. It's just that that parabola's inverse doesn't pass the vertical line test. So in order to have an inverse that's a function, the original must have been 1-to-1. We talked about the reflection. If f is continuous, then f inverse is also continuous. That's going to be helpful for us when we talk about taking derivatives. If f is strictly increasing, then f inverse is also strictly increasing. So that's helpful because that means that if f prime was positive always on f, then f prime will be positive always on f inverse. Decreasing and decreasing has the same relationship. This is where things get interesting. So if f is differentiable at c, so f differentiable at c, that means that f prime of c exists and is not equal to 0, then f inverse is differentiable at f of c. So that means that f inverse prime of the output exists. Okay? And that's because on the original, we would have had the point c, comma, f of c. And on the inverse, we would have had input f of c, output c. Oftentimes students do better if I change this f of c to be b, which means that on this statement, instead of f of c, let's talk about the letter b. Okay? So the derivative at the input implies that the derivative of the inverse at the output exists. Whew. It's a lot, but we're going to be okay. All right, the next two examples are a nice review from pre-calculus about how to actually find that inverse. So step 1, replace f of x with y, which we did here. Step 2, interchange x and y. So x replaces the y and y replaces the x. Step 3, solve the equation in terms of for x in terms of y if possible. So we isolated y. And then the last step is just function notation. Go back to f inverse. And so what we have just found is that the inverse of x to the 5th minus 4 is the 5th root of x plus 4. Think about how that plays out, right? We have a subtract 4, and in our inverse we have a plus 4. In our original function, we have raising to the 5th power. In our inverse function, we have taking the 5th root. Pause the video and try for yourself finding the inverse of this f of x, 2x cubed minus 1. Go ahead and pause. Try for yourself. Okay, showing the steps, we replace f of x with y, switch our x's and y's around, solve to isolate that y, and then rewrite our y with function notation. Again, think about what you noticed. We have 2 times x to the 3rd minus 1. And here we're undoing those steps. We're adding 1, we're dividing by 2, and we're taking a cubed root. This inverse undoes the original function. Also, think about your order of operations. In the original function, you would start by taking x, raising it to the 3rd. So we go x raised to the 3rd times 2 minus 1, which means when I go to undo that, I need to start at x, I need to add 1, I need to divide by 2, and I need to take a 3rd root. Okay, because your directions, these were the directions going forward. These then are the directions in reverse. How do you undo your steps that you took? All right, these next 7, okay, we've got a lot of graphs here, or a lot of equations here. I want you to pick your favorite color out of red, orange, yellow, green, blue, purple, or pink. And just pick one of them and find f inverse. So pause your video, find the inverse for whichever one you think is your favorite color, and then we'll come back together. So red, orange, there's yellow if you need it, green, blue, purple, or pink. Pick which one you like best, find the inverse, unpause when you're ready. All right, let's find some patterns. Go ahead and check your answer based off of the color that you chose. You do not have to write all of these down. There's the answer for the yellow if you need it. What I want you to take a second though is to look at each one of these and how they start. So f of x being 5x plus 2, f of x being negative 4x plus 8, every single one of these functions, f of x, is part of the linear family, a line. Look then at what happens when you take the inverse when it comes to the slope. F inverse, when we had 5x, becomes 1/5. F inverse, when we had negative 4x, becomes negative 1 over 4. When we had 3x, we end up with 1/3. When we had negative 2x, we ended up with negative 1/2. Do we see a pattern forming? And if you're saying, Ms. Schwartz, that looks like a reciprocal, you would be correct. Now be careful, because opposite reciprocal is perpendicular lines. Just straight up reciprocal is the slope of the inverse line at a given point. So let's say I started with f of x equals mx plus b. Well, I switch my x and my y. So my plus b, I get x minus b equals my, which means that 1 over m times x minus b over m is equal to my f inverse of x. Because we're studying derivatives, we want to focus on the slope. So the inverse slope is the reciprocal when we're talking about a line. Can we expand this definition to be for any function in mathematics? And if you're sitting there thinking, well, yeah, Ms. Schwartz, because we started talking about the fact that if you zoom in close enough on any smooth curve, what does it look like? It looks like a line. All right. So if f and g are inverse functions, so g is like the same thing as f inverse, then when we compose them from pre-calculus, we end up with this information, okay? F of g of x is equal to x, and g of f of x is equal to x, because it's like tying your shoes, then untying your shoes, you're right back to where you started. It's like walking to school and then walking back home, you're right back to where you started. So if we think about this from a calculus perspective, I'm going to take the derivative of f of g of x, because these are inverses of each other. Using the chain rule, I get the derivative of the outside, leave the inside alone, times the derivative of the inside. Then I wanted to find, I told you this whole day was about finding the derivative of the inverse. Well, the derivative of the inverse would be g prime. Derivative of the inverse. And that was my goal all day today, was how do I find the derivative of an inverse function? Well, to do that then, I just need to divide by f prime of g of x. Something that we want to note then is on the original function, f, we would have had the point a comma b, in which case f inverse, which is really g, has the point b comma a. So g prime of b is equal to 1 over f prime of g of b, which is really a. And if you're like, what just happened? That's okay. We're going to practice this. But notice that we come out with 1 over. We come out with a reciprocal slope. The slope of the inverse is the reciprocal slope of the original if we are talking about zooming in on one specific point. This only works if we're looking at one local point because of local linear features. Okay? So this is not just the derivative of g is 1 over the derivative of f. No, 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 no. The derivative of g at b is equal to 1 over f prime of a. Okay? What this does for us is it means we don't need to find an equation to get f inverse. We don't need to do all of those steps from pre-calculus in order to just talk about the slope. All we need is if I want the slope f inverse prime, the slope of the inverse, at a given point, it's 1 over the original slope at the buddy. Okay? So in this situation, f inverse has a coordinate point of a, b, right? Because the input into f inverse was a, has an output of b. That means that f, the original, has the point b A. Next video will take you through our practice problems.